All right, guys, starting a new chapter, probability distributions. Probability distributions, still working on some probability stuff like we have been, but combining it with some new stuff too. So let's just check it out. This is the chapter problem. As you know by now, every chapter has a problem you see over and over again. This is another version of, well, it's called an XSort method where, let's just read right here. The Microsoft XSort claims it increases the chances of having a baby girl. YSort claims it increases chances of having a baby boy. Current results from the XSort from 945 couples are 879 baby girls. That's pretty good. We usually expect somewhere around 472 or 473. Can we conclude that XSort is effective? Or is it just a chance sample result? Do we get a sample that just like it was crazy with girls? Our goal is going to be to determine whether the observed results differ significantly from results we would expect from random chance. That's pretty much what we do in stats all the time. Is it just random chance, or is their product really effective based on statistics? All right. Probability distributions describe what will probably happen instead of what actually did happen. And they're often given in the format of a graph, table, or formula. We're going to look at them in two areas really, and that's a graph and a table. A table more than anything, but a graph occasionally. You're going to see some of those coming up. Okay, combining descriptive methods and probabilities. This is describing the very first part of that we did this year versus what we do now. Because we're going to talk about what we expect with the relative frequency. So what we did first, find couples, number of girls for couples having children. So we do a random sample. It says right here, chapters 2 and 3. Here's what we did. We collect sample data from families with 2 children. Random sample, then find stats and create graphs. So what we did is we found couples with 2 children, and this is how many girls they had, either 0 girls or 1 girl or 2 girls, and this is how many. This was our frequency distribution. Remember we did frequency tables and frequency distributions before fall break. And we learned how to find the mean of that and the standard deviation of that. In chapter 4, we did this. We found the probability of each girl. Remember we did like BBG, GGG, BBG, GBG, all the BBGs. And we found the probability of 0 girls or 1 girl or 2 girls. Now in this chapter we're starting today, we're going to create a model of expected results and then find parameters. And by parameters we mean the mean and standard deviation of our probability distribution, that's what a probability distribution looks like. Kind of like our frequency distribution, except it has probabilities in it instead of frequencies. All right. This section introduces the important concept of a probability distribution, which gives the probability for each value of a variable that's determined by chance. Give consideration to distinguishing between outcomes that are likely to occur by chance and outcomes that are unusual. We're going to figure out when they're unusual in the sense that they are not likely to occur just by chance. And I'm going to be honest, we're going to spend the rest of the year doing mainly that one thing right there. It gets a little more complicated as we go. All right, some words you have to know. Like these are, make sure, if I were going to give like a notes quiz tomorrow, these would be on there probably, or at least some of them. A random variable. A variable, typically we're going to use X all the time, that has a single numerical value. Determined by chance for each outcome of a procedure. So, but the girls a minute ago, the random variable was 0 and 1 and 2. Probability distribution, a description that gives the probability for each value of the random variable. So, often expressed in the format of a graph, a table, or formula. Like I said, we will do the table the most. We will look at some graphs though. So make sure you get those definitions really good. A couple more coming up. Discrete random variable. We did these 2 words, discrete and continuous, very early near. There were like 100 tests already. Actually, we've only had about 8, so whatever. Discrete random variable, either a finite number or values of countable. With the girls, the 0, 1, and 2 were discrete because you could count them. You have 0 girls or 1 girl or 2 girls. There could be infinitely many, but you can still find them by counting. Continuous has infinitely many values, and those values are associated with measurements like arm length on a continuous scale without gaps. Like, for example, discrete has gaps like 1, 2, 3. You skipped 1.5, 2.5. Continuous, you skipped nothing, and that's why it's continuous. There's no gaps. Probability distribution requirements. Okay, one part of your assignment tomorrow is they're going to give you some distributions and ask you, are they probability distributions? There's three things that must happen, must be true. First of all, there is a numerical random variable. With the girls, it was 0, 1, 2. It must be a number. It cannot be a category. It can't be a categorical variable. Number two, if you add up all the probabilities, you must get 1. Remember the symbol sigma, that's sigma. If you add up all the probabilities in your distribution, it must equal 1. Every probability must be between 0 and 1. 0 being the smallest, 1 being the greatest. So those three things must be true for you to have a probability distribution. Graphs. When you see one as a graph instead of a table, it's going to look like this. It's going to look just like a histogram, except it's a probability histogram. And the only difference being this side over here, instead of being the frequency is how many times it occurred, it's the probability that that occurred. The bottom is still the same. These are your random variables that we talked about a second ago. These, as a matter of fact, this histogram says for number of Mexican American jurors among 12. So you have like a 30% chance of getting 10 of them, maybe a half. Looks like a half, maybe a 0.5% chance of getting 12, which is very rare. Very small chance of just getting 4. So I guess it depends on where you are, but it's very similar, except you got probability in a random variable instead of the frequency in a random variable. Okay, this is huge. Make sure you get all these down. Again, if I was going to give a quiz tomorrow, oh my gosh, this would be on there for sure. The way you find a mean of and standard deviation of probability is you do this. Remember, this is sum. You multiply your random variable times your probabilities, and you add them up. You multiply, then you add. When you're finding, this is variance. There's two ways to find the variance. To be honest, this one says shortcut, and that's okay. I still like this one a little better, and that's probably the one I'm going to use. Basically, what you do is you do this. Once you find your mean, you take each random variable, subtract it from the mean, multiply it by the probability, and then add them all up. You can also do it this way. You can just square each number, multiply by the probability, add those up, then subtract the mean. Remember, that's mu. Mu means mean squared. So either way you want to go is fine. And you always get standard deviation by taking the square root of the variance. It's always the same. Always. Did I say always? It's always the same. Expected value of a discrete variable is really, it's just the mean. If you recognize this from the last slide, that formula right there, this big formula right here with the big E, expected value, that's the mean. So what you expect from a probability distribution, the expected value from it is just the mean. Keep that in mind. Okay, let's just try one here. Okay, so what I need here to find the mean is I need to do the x times the probability of x. That's how we're going to find that. Says p of x, p of probability of x. Let me make that look a little bit better right there. If I don't pick up my stylus and high enough, it does that. Okay, so to find the mean, I'm going to do 0 times 0.25, that's 0. 1 times 0.50, that's 0.50. 2 times 0.25, that's 0.50. And I'm going to add, this says total down here, I'm going to add that up, 1.00. Guys, that's the mean. That's how you find the mean. You multiply x times the probability and you add them up. So that's my mean, or my mu. My mu is 1. To find the variance, I'm going to do this right here. I'm going to do x minus the mean, square it, times the probability. So it's going to look weird here. I'm going to go x, which is 0, minus the mean, which is 1, which gives me negative 1, times the probability, which is 0.25. Forgot to square the negative 1. Negative 1 squared is 1, so I get 0.25. I'm going to talk you through this other one. You do x, 1, minus the mean, 1, which is 0. 0 squared is 0, times the probability. It doesn't matter. It's still 0. Now take the 2. You do 2 minus the mean. 2 minus the mean is 1. That's 1. Square it. It's still 1. Times the 0.25, which is 0.25. And I'm going to add those up. 0.50. That is the variance. Now the variance isn't what they asked me for the variance. 0.50. To get the standard deviation, I would take the square root of the variance. And everybody knows the square root of 0.5 is like 0.707. There's your standard deviation. All right, so that's how we're going to calculate it in our table if we know, well, once we have our probability distribution. Okay, the main reason we're going to do that is so we can identify unusual results. So we're going to use the range rule of thumb. Guys, we used this before fall break. Hope you remember it. According to the range rule of thumb, most values are within 2 standard deviations away from the mean. All right, so we're going to identify unusual as those values. So the max unusual, we're going to do the mean plus 2 standard deviations. For the minimum unusual, the mean minus 2 standard deviations. So let's look at the girl problem again, or the probability that we just did. So the example we just did, we found out that the mean was 1, standard deviation is 0.7. So if I do, to find the max and min unusual values or usual values, I'm going to take the mean plus 2 times standard deviation, which I did right here. Got 2.4. The minimum usual, I did the same thing, mean minus 2 times standard deviation. I got negative 0.4. So what that means is anything between those two numbers we would consider usual. And in our table, of course, it's only two kids. So we had 0, 1, and 2. All of those numbers are usual. 2 is not bigger than 2.4. 0 is not less than negative 0.4. So with only 2 kids, there's no unusual values for how many girls you can have. Now, the more kids you had, the better the chance you're going to have some unusual ones. All right, identifying unusual results based on probability. Doing the same, still unusual, but now we're doing probability instead of just looking at 2 times standard deviation. Let's read this problem. If under a given assumption, such as the assumption that a coin is fair, okay, we're assuming the coin is fair, the probability of a particular observed event, and here's the observed event, 992 heads and 1,000 tosses of a coin. That probability is so small, we conclude that the assumption is probably not correct. And our assumption was the coin is fair. So we're going to assume, because we got this probability, 992 out of 1,000, that it's not a fair coin. The assumption is not correct, that the coin is not fair. And that we're going to use probability to do that. And this is how we're going to do it. We're going to use the number, guess what, 0.05. The way we're going to tell with probabilities that stuff is unusual or outcomes are unusual, unusually high if the number of successes, X or more, is less than 0.05. Unusually low if successes among X or fewer, that's important. X or more, X or fewer, is also less than 0.05. So we're going to use that 0.05 barrier once again to tell us if something's unusual probability-wise. The other way was the standard deviation way, the probability based on a probability distribution. So we'll work on these tomorrow. Make sure you get some good notes for your little quiz when you come in, and I'll see you then.